So in this video, we're going to talk about the assumptions that compartmental models make, what these assumptions sort of mean about how they represent a simplified reality, and some ways you can think about either thinking about or mitigating these types of assumptions. So the first assumption, and the one people often think of as sort of the characteristic assumption of compartmental models, is random or homogeneous mixing. And this is that everyone mixes randomly with everyone else in the population at the same rate. Essentially, if you think about this metaphorically, what you're doing is you're taking all your little simulated people, you're putting them in a box, then you're shaking that box and seeing who comes in contact with whom. You can adjust this a little bit by creating more compartments or more interactions between compartments. So for example, an STI, a sexually transmitted infection model, may have men and women and then have contact rates for both same-sex and opposite-sex pairings between those two compartments. But within each pairing type, people still pair randomly. This is obviously incorrect. If we think about how people interact with each other, we have friends, we have coworkers, we have family members, we have specific people we interact with, but how much it matters depends on the population and the disease. Generally speaking, for larger populations, this is less of a big deal. And then also this is less of a big deal for infections that are capable of transmitting without prolonged contact. So things like measles, COVID-19, or influenza, where the sort of transient interactions you have with people over the course of the day, who you bought lunch from, who you interacted with as you passed them by in a hallway, things like that, count as a sufficiently prolonged contact to create infection versus something like a Staph aureus infection that requires prolonged skin-to-skin contact, where the fact that people don't mix randomly actually is quite important. So there's also compartmental homogeneity. And this is that everyone within a compartment is the same. So everyone in the susceptible compartment is equally susceptible. Everyone in the infectious compartment is equally infectious. There's no ability to track someone who is in the susceptible compartment because they're a newborn versus someone who their immunity has waned. So they were in the R category and they have moved back to the susceptible category. You can't keep track of those things. We can't keep track of if someone has been infected a bunch of times versus this is their first infection. This can often be a problem. We sometimes want to track people. So for example, when modeling a healthcare-associated infection, when you recover from your infection, are you still stick with what you had that put you in the hospital in the first place? So if you had acute kidney failure, you got a hospital-acquired infection, we treated you for it, you've now recovered, do we discharge you or not? The problem is if we just dumped you in a category that said, oh, you've just got a hospital-acquired infection, we've lost that information about who you were before. And this is often a fairly significant problem. Another assumption in all of these models is exponential waiting time, or that these are Poisson processes. This is that we assume the time spent in a compartment is exponentially distributed. If you're familiar with survival analysis, you can think about this as the hazard of transition between compartments is uniform. Everybody has the same probability. This can be translated in a discrete time model to a number of people moving between compartments, and this is called a Poisson process. This is very analytically convenient. It's also easy to get parameters from a parametric survival model. You just fit an exponential model for times, and you've got an exponential time. Or a Poisson model for counts. Again, you get the parameters you're interested in out of this. Again, though, this is a very strong assumption, and it's possibly wrong. So there are ways to get around this. So if you add multiple compartments, so for example, if we think about a latent time compartment, and instead of having you go from S to E to I, you go from S to E1 to E2 to E3, creating 3 exposed classes, we can turn the waiting time from exponentially distributed into gamma distributed with a shaped parameter k, which is equal to the number of compartments, 3 in our example. So this figure on the slide shows what those gamma distributions look like. So for example, our distribution would be this one, this third one, where you've got a less exponential. You're starting to look like it's sort of a truncated distribution. And as you create more of those compartments, you start getting a sort of much different shapes. This is nice. This is a very powerful tool that can give us some very strong means of manipulating waiting times, but it often doesn't matter. So during my dissertation, I went through every waiting time I could in the model and tried to fit them to a number of different gamma distributions. And it turns out all of them were best approximated by an exponential distribution. So my choice was essentially an exponential distribution or a gamma distribution with shape of 1, which is the same thing. Those fit better than a gamma distribution with shape 2, which is sort of the next least complicated choice. So this is, again, something that you can check, though, which is the nice part about it, is you can actually look at your data, look at some of the things you're estimating for parameters, if you're estimating them through sort of statistical models, and actually evaluate the appropriateness of this assumption. The last one we're going to talk about is density versus frequency dependence. Transmission is typically modeled in one of these two ways, density or frequency dependent. Density dependence says that the per capita contact rate between susceptible and infected individuals depends on population density. So as density goes up, so does transmission. When we look at this in terms of an ordinary differential equation and the equation for the I category, di dt equals beta times s times I. Frequency dependence, on the other hand, the per capita contact rate between susceptible and infected individuals does not depend on contact density. So essentially, as the world gets more dense, transmission rates do not necessarily increase. So when we model this, instead of just beta times s times I, it's beta times s times I over n. There are more exotic forms, but these two predominate. So if we look at this figuratively, frequency dependency, as you can see, population density is flat. We'll talk a little bit about that very sort of left-hand side, and then density dependence, the transmission goes up as you get more people. So the question that naturally arises from this is, okay, but how do I decide? This is usually a very disease-specific decision. It's something that you as a subject matter expert, or if you're working with subject matter experts, something to discuss. So imagine an airborne disease like COVID-19 or influenza. It might make sense to model this as density dependent. The more people there are in a given area, so the higher density, the more likely is transmission is to occur. So if you think of a room that's sort of slowly filling up with people, and I say some of these people have COVID, you probably get more and more nervous as more and more people in the room, more and more people fill the room. In contrast, if we imagine a sexually transmitted disease like HIV, this may be more sensible modeled as frequency dependent. The amount of sex a given person is likely to have is probably not purely a function of how many people are around, and what's more important is the proportion of their partners, which is likely probably a fixed rate, who are infected. Mate selection is sort of one of the canonical examples of frequency dependence. Note that this might not be the case in very small populations. So, for example, if the population of potential partners goes from 1 to 2, that may genuinely change how many partners one has in a way that's not necessarily true if you go from 10,000 to 10,001. So that's sort of a brief overview of the various assumptions of compartmental models that we'll explore more in the workshop itself. And thank you very much, and I'll see you in the next lecture.